So we're back with forces acting at a distance, part 2. So we went over force, again, as a push or a pull. These are forces that don't have to be touching to be acting on you, forces that act at a distance. And the two we're going to talk about today are electricity and magnetism. Both electricity and magnetism create positive or negative charges, which can attract, so pull, or repel, push. So those positive or negative charges will either attract, so pull together things, or repel, push apart things. So how do these charges work? How do you know if it's going to attract or repel? Like charges repel. When you put two negatives together, they don't want to be together, so they will push each other apart, okay? Opposite charges attract. When you put a positive and a negative next to each other, they are really excited about it. They will pull each other closer. So we're first going to talk about magnetism and magnets. Magnets create a magnetic field. For example, you can have a bunch of magnetic particles near each other and then put a magnet in present, and all of a sudden you've got this really cool lined up magnetic field. This magnetic field causes anything magnetic to align or line up within its magnetic field. This is used for things like compasses. The compass needle is a magnetic object, so it lines up with Earth's magnetic field. Earth is a big magnet. Remember, back in earth science, you learned that Earth has that iron core, that solid iron core. That iron's magnetic. That's what's causing a magnetic field. Other practical uses, obviously, you use it to stick stuff to your fridge. Some security systems work by magnets when the magnets aren't being attracted to anything, like a window's opened or a door has opened. That's when they change, that's when they sound the alarm. So this is a really simple but the biggest key point about magnetism, which is why I gave it its own board. So this magnetism, key important point. The closer you are to a magnet, the stronger it is, and the farther you are, the weaker it is. This is called an inverse relationship between distance and magnetism. Again, closer, smaller distance, bigger magnetism, or bigger distance, smaller magnetism. Okay? You can actually try this yourself. If you're watching from home and you have a fridge with magnets on it, you can just pull one of the magnets off. You'll notice that the further you get away, you don't even notice that there's something magnetic there. And then the closer and closer you bring it, eventually you'll feel that pull, okay? Or if you're at school and you can find a dry erase board, one of the whiteboards, and a magnet on there, again, the closer you are to it, you can feel that pull. You pull it further away, and that magnetic force gets weaker. So with electricity, there's going to be two big kinds of electricity we're going to talk about. Electric flow. This is like the electric current. This is the movement of the electrons through a current that you typically think of, like lights a light bulb. And then there's also static electricity. We're going to talk more about electric flow on the next slide, so don't think that's all the information you're getting. As far as static electricity, it's an electric buildup on an object. You might have experienced this sometimes where after you've worn shoes or socks and you've walked across a carpet and you've scuffed your feet, and then you go to touch a metal doorknob and it will shock you. Ouch! That was static electricity moving from you to the object. Okay? So the electric buildup on an object, and again, the charges don't move until they have somewhere to go. Just like the charges on you that built up when you walked across the floor didn't move until they had somewhere to go. They didn't move until you touched that metal door handle, and now you could create a flow of electricity. Okay? So they were just on you. So the reason static electricity is considered a force, a push or a pull, is because that static electricity can build up, and if it builds up a bunch of like charges, or if it builds up same charges, those same charges would attract again, and those like charges would repel. For example, you can try this yourself. You get a balloon and you rub it on your hair, rub, rub, rub. When you pull your hair away, your hair will actually be similarly charged. They will all be negatively charged, so your hair will repel each other, but the balloon is now positively charged. The positive charge of the balloon is going to attract your hair to it. So as far as electric flow, we use that electricity flow to make circuits. These circuits are what powers pretty much everything. So the circuits, there's working circuits and non-working circuits. The proper terminology for that, if you have a working circuit, it's considered a closed circuit, which might sound weird, like when a store is working, we don't call it closed. But if you look at how it looks, it's closed. It's a closed circle. Nothing else can get in. Nothing's in the way of it. It's closed. Whereas a circuit that doesn't work, so if there's a missing spot, it's called an open circuit. It's open. Things can get in. It doesn't work anymore. So that's just open and closed circuits, or circuits that work and circuits that don't work. As far as how we arrange these circuits, there's two different ways we can arrange it. There's like the old school way. Think about your Christmas lights. If you ever put Christmas lights out and you have those Christmas lights where as one bulb burns out, they all burn out. Those lights are arranged in a series circuit. It's connected, all of the lights on that are connected to each other, and if one goes out, they all go out. For example, in this one, everything's connected, everything's working, they're all lit up. Whereas in this one, this light bulb broke, now none of them are working. Okay? Obviously that was bad. You couldn't have a whole neighborhood of homes with a series circuit, because if the power in one person's house went out, like they didn't pay their power bill and now the power went out, the houses, all of the ones on that circuit would all go out too. That wouldn't work. So instead, there's a different way of wiring it called a parallel circuit, and where it's each light or each thing that you're powering connects back to the original power source. If one goes out, the other ones stay lit. So right now, they're all connected to each other. If I were to erase this one, the other ones still stay lit.